Thank you, Nicolas, for the introduction, and thank you to the organizers for inviting me today. Before I start, I wanted to acknowledge the phenomenal contributions that the students involved in this project made. So you can see their photos here, Jonas, Tom, Hannah, and Nick, as well as our collaborator, Gabriel. About a year and a half ago, me and my students started thinking about the implications of AI agents to cybersecurity, and there has been, since in the recent sort of last couple of months, last year, been a lot of good work starting to study this intersection. I wanted to highlight a few examples here. The first category of work is really looking at the ability of AI agents to assist or complement human cybersecurity experts as they conduct penetration testing. So I put a few examples here, Auto Attacker, Artemis, and Incalmo, some of which is by some of the organizers of this conference. And I think here what's important to take away is the focus is really on using some of the larger models to assist with these tasks. And in parallel, there has been a line of work on self-replicating prompts, where the idea is really to show that the language model itself can be a vector for propagation of malware. And so this is work by Ben and his collaborators, which I'm sure a lot of you are familiar with. In our case, we wanted to understand how AI agents change sort of the ability of adversaries to construct malware that is not only able to exploit machines, gain control of them, but also to use the control of these machines to then serve as a launch pad for attacking other machines. So this is the definition of a computer worm. And we've seen many examples of this in the past. I wanted to highlight one here, in particular, the WannaCry ransomware attack, because I think it provides very useful context for understanding some of the implications of our own work. So this attack was launched in May 2017. It exploited a vulnerability called Eternal Blue, which allowed the attackers to gain control of Windows machines, to encrypt the files on these machines, and then they would ask the victims for a Bitcoin payment before getting access back to their files. So what's interesting here is the timeline, in the sense that this vulnerability is believed to have been discovered by the NSA, which they kept secret until they realized that it had been leaked, at which point they notified Microsoft, which developed a patch which was available in March of 2017. And despite this patch being available, in May 2017, when the worm was launched, it was able to compromise hundreds of thousands of computers in over 100 countries and create billions of dollars of operational damage. In particular here, I put in the bottom right corner a couple of examples of very large organizations whose operations were disrupted by this ransomware attack, including the NHS, so the hospital system in the UK, FedEx, the Deutsche Bahn in Germany, or TSMC. And what's important here is that these traditional computer worms could be patched. Their propagation could be interrupted by patching the systems. And here you can see how important it is to deploy these patches in a timely manner to close that window of opportunity for the attackers. And these traditional worms typically exploited a fixed set of vulnerabilities. So we're talking about a handful of vulnerabilities, so you know exactly which patches you need to deploy to interrupt their propagation. What we found in our work is that with AI agents, attackers can now develop a new class of computer worms that is able to identify specific vulnerabilities for each of the machines that is being targeted. And what this means is that AI is essentially generating a tailored attack strategy for each of the victim devices. This changes sort of the defense game because now you're looking at a much larger number of vulnerabilities that potentially expose these machines to these kinds of worms. And importantly, our work made this demonstration using an open-weight large language model. And this is really important for a couple of reasons. The first one is the fact that the model is open-weight means that the AI agent is able to replicate itself, but also the model itself. And so as it's propagating on a computer network, the agent is going to bring the language model with itself and launch essentially LLM inference servers on any machine that is capable of running an LLM, and that adds compute capabilities to the worm's infrastructure. This allows it to sustain its reasoning, but also to expand the reach of its attacks. And the second important consequence of using an open-weight language model is that the AI safety safeguards that are being put in place to protect closed source models are irrelevant to preventing the propagation of the computer worms as we've demonstrated in this work. So things like service refusal, rate limiting, they're all irrelevant in this case because anyone can download the model from the internet. So of course, being academics, when we start thinking about an idea like this, there are a lot of dual-use considerations to be taken into account, and we have to think about the ethics of doing this work before we even begin looking at this. Here, just let me walk you through our analysis. The positive implications of the work are that we're helping society gain awareness of this threat and give society the ability to prepare itself to defend against these generative adversaries. Of course, the negative consequences are that malicious actors now have access to information about how to use AI for nefarious purposes, and so they could use this information to create actual malware. So the way that we've mitigated this risk is by looking at the entire life cycle of the project and making some deliberate decisions in the way that we approach this project. In terms of methodology, we explicitly did not design the AI agent to be stealthy. This is by choice because we believe that the experiments we've conducted are sufficient to demonstrate the threat, and adding the stealthiness would only sort of help malicious adversaries. Deployment was also very careful in the sense that we conducted all the experiments in a contained virtual network. And I'll explain in the next slide which kinds of controls we put in place at the hypervisor level to isolate the experiments. We also paid particular attention to who had access to the worm implementation itself, the code base that we were working with. And this access control was done with institutional oversight by the University of Toronto. Once we were ready to share our results more publicly, we first disclosed this to Canadian authorities to give them a chance to prepare, as well as to give them a chance to guide us in the responsible disclosure process. And as part of the preparation for releasing the results, we decided to withhold some of the details in the manuscript. It's clearly marked in the manuscript when we redacted something. The idea here is to remove details that are not necessary for other scientists to understand the threat and to design defenses, but withhold these details if they're helpful to bad actors. And so given all of this, we believe the research was justified, and this scientific characterization is something that's beneficial for society. In terms of the containment, you'll see in some of the rest of the talk that the design axiom that we followed is that all containment enforcement needs to reside in a higher privileged domain than the agent. And that's because we have sort of the ability here with an agent to modify some of the containment measures themselves if they're within the same domain as the one the agent is operating in. So we use a hypervisor, and all the agent activity is contained within virtual machines on this hypervisor. The 4 layers of containment are first network-level traffic filtering. This is to limit traffic leaving the VMs themselves. Then anytime that the agent needs to interact with packages or dependencies that need to be resolved before setting up the code itself for the agent, we do so through a proxy. And then we have a last layer which isolates any remaining egress path at the server level of the lab machines themselves. And so with this sort of layered approach to defense, we prevent the agent from propagating outside the virtual environment in which we're running these experiments. We also added a last component, which is this attestation service. And here the idea is really to prevent accidental launch of the agent by some of our team members outside the environment. And so the way this works is essentially before the agent starts executing its algorithm, it requests a certificate from this attestation service. The attestation service will check that the agent is actually running within the environment and also check that all the containment enforcement is healthy in the sense that it's properly configured, and that's coupled with a watchdog that restores any disrupted configuration on a regular basis. So this is a representative example trial from our experiments. What you can see in the center here is the machine from which the worm is launched. And as you get away from the center, the agent is propagating on the computer network. It's important to notice the shape of these nodes because it illustrates the heterogeneous nature of this computer network. We have machines that are different Linux distributions, Windows machines, but also IoT devices like printers or cameras. And this really shows you how ubiquitous the attack surface is for these AI-driven worms. And even machines that are sort of less interesting targets, like a printer, can be used as a stepping point to attack additional machines. Something else that I wanted to highlight is that we are not only able with this agent to exploit sort of bugs in software, well-identified vulnerabilities, but also misconfigurations that would be sort of weaknesses due to human error. So a good example of this is SQL injection. Here, the machine that I'm pointing at is the agent is gaining its initial foothold through an SQL injection, which of course is the result of the human implementing a system that's not properly sanitizing its inputs. Similarly here in this machine, the agent is reusing a credential that it has found on a different machine to be able to gain an initial foothold on that victim. And so that also demonstrates human error. And it also demonstrates the ability of these different agents to orchestrate their actions. And I'll explain how we do this a little bit later in the talk, where the agents running on different victim machines are coordinating to exploit additional machines. That specific victim was then the agent used a one-day vulnerability to escalate privileges and obtain administrative privileges on the machine. Here, the reason that I pointed this out is that this vulnerability was discovered in April 2026. So we're in June 2026. This was literally days before we ran this experiment. And this shows how easy it has become for attackers to take vulnerabilities that are discovered and exploit them at scale using AI-driven malware like this. So why had the community sort of underestimated the implications of open weight models for cybersecurity. I think the underlying problem is that the way that the AI safety community thinks about cybersecurity hasn't really captured the economics of cybersecurity properly. There is a lot of focus on frontier models executing cyber attacks end-to-end, and in particular also on these models discovering zero-day vulnerabilities. In practice, if you look at the real world and attacks, attackers are constrained by time and resources, and they will very often rely on one-day vulnerabilities rather than zero-day vulnerabilities. That is the reason why I used the WannaCry ransomware example earlier in the talk. The vulnerability had been known for months and patched, and yet the attack still has such a devastating impact. And so I think it's really important that we consider the attack surface that's been ignored until now, and the attack surface that these open weight models represent. So the main challenge in doing so is that these open weight models, of course, have limitations compared to some of the larger models. In particular, it's really more difficult for them to reason over long trajectories, to follow multi-step attacks when you have a lot of steps. It's also very difficult for them to analyze a lot of information all at once. They have a shorter context window, so you have to be a lot more strategic about what the agent is using to predict its next action. And the way that we address this is using a harness. I'm going to describe it next, but essentially you can think of this as encoding a lot of cybersecurity knowledge to structure how this AI agent is going to go about sort of maximally propagating over the network. And so here on the right, what you can see is the different phases that we structured the workflow in. And these essentially provide the agent with intermediate goals that it needs to achieve on each of the machines in order to be able to replicate on this machine. So the first phase here at the top is network discovery, where the agent is essentially trying to identify potential target machines on the network. Then it's going to interact with one of these machines and make observations about the services it's running, ports, et cetera, to identify a vulnerability that could give it initial foothold on that machine. Once it has gained the initial foothold, it's going to do another round of discovery to now formulate hypotheses for which vulnerabilities could allow it to escalate privileges to essentially get pseudo access, for instance, on a Linux machine. And once it has gained control of the machine, it can begin the replication phase. There are two variants for that replication phase. Either the agent is going to replicate itself alone if the machine doesn't have a GPU accelerator, or it's going to replicate itself and also start an LLM inference server with the open weight model that's powering its reasoning if a GPU is available. Now, the biggest challenge we faced was really to design the harness in a way that addresses the very short context window that the open weight language model has. And so here I wanted to give you a little bit more details as to how we chose what information to present to the model at every single step of the attack so that it can take the right actions. So as I mentioned, the phases provide very high-level structure in terms of what are the intermediate goals of the attack. Within each of these phases, we have a reasoning graph, which the agent iterates through these different nodes of this graph to actually interact with its environment and take the observations it's collecting and store them in a memory. So this is what you see here in the middle, where essentially within each of these phases, the workflow is similar. First, there's a planning node, and then a judge node that will decide what observations are relevant to decide what action to take. Then this action is taken with the help of an external tool. This produces information that is summarized and then saved into the memory. and then used to decide how much progress did the agent make towards the goal of this particular phase. The memory itself allows us to store information on a much longer time horizon than what the model can retain itself. And so we had to structure it with sort of 3 hierarchical levels to be able to retrieve the right information at different phases of the attack. The first, the highest sort of abstraction is sort of phase level memory, where we're keeping track of which phase we're in, what are sort of historical observations we've made. Then we have a level of memory that is specific to each target machine, where we keep track of information about that machine itself, so things like the operating system, any credentials, et cetera, and also hypotheses that we've made about what vulnerabilities this machine presents. Then we have a vulnerability level memory, which keeps track of outputs of sort of the agent's action calls, and also a failure count. This is really important because the agent has a tendency to keep trying to exploit the vulnerability even when it's clearly not going to be able to. And so this aspect of the memory allows us to rotate through vulnerability hypothesis and try other hypotheses if that vulnerability is not exploitable. And then the last part is sort of the set of tools that we give access to the agent to interact with the environment. And here, the common design sort of consideration of these tools is really to address the heterogeneous nature of the network. So things like establishing remote command line sessions can be very difficult for an open weight model, especially when these sessions need to be held concurrently. And so that's why we have tools to do this. Same thing with transferring files. When you want to transfer the weights of the model itself, this is something that's a bit challenging for the open weight models. And then finally, the beacon allows other instances of the agent to easily get access to a machine that's already been compromised. And this is really important because of this swarm orchestration layer that I presented earlier. And here I want to give you a bit more details. So this idea here is really that we want to establish a tiered infrastructure where the agent is not only able to compromise machines that have a GPU, but also machines that don't have a GPU. And the lower compute nodes will still be used as a launching point for attacking additional machines on the network. And so this requires here the ability, if you look at this printer here, to tunnel the inference requests that this node is making back to a node where we did have access to a GPU. So you can see in blue, these queries to the LLM are actually being redirected by that orchestration layer back to a node where the agent had access to an LLM inference server. And that's how it's able to make predictions with the model. This also comes with a load balancing feature, because as the agent propagates on the network, gets access to multiple GPUs, you want to be able to distribute the LLM inference queries across these different nodes. And you also want to avoid having multiple agents attacking the same machine simultaneously, because we observed this leaves the machines in an unusable state or crashes them very often. And so we have that coordination implemented. And then previously I mentioned this credential reuse attack. This is where we implement this at the orchestration layer, where we propagate these credentials as soon as they're discovered on one machine, so that agents on other machines also have access to them. So put together, this is what our results look like over 15 independent trials. The line that you see at the very top is the number of machines in our test bed. So we have 33 machines. The blue curve shows you when the agents correctly identified the vulnerability. In orange, you see when the vulnerability was correctly exploited, and so the agent gained privileged access to the machine. And then in green is when the agent was able to self-replicate on that machine. And so if you look at the very right-hand side, you have about 60% of the network that the agent was able to self-replicate to. And on the horizontal axis is time. So you can see that this is taking a couple of days. Now, looking a little bit more at some of the reasons for the agent failing, you can see that at the vulnerability identification level, there's relatively little failure. And most of the failures that we observed were when the agent fixated on a service that is actually completely benign, like a web server, and failed to identify the vulnerability because of that. At the exploitation phase, there's a lot of attrition. This is where the limitations of open-weight models really come clearly. There are really two main reasons for this attrition. One is that in some cases, the agent failed to identify the endpoint with which the vulnerability needed to be exploited, despite having correctly identified that vulnerability. And then in a lot of cases, the agent failed to form the payload itself. And so this is just difficulties in maintaining the syntax or making very large outputs with these open-weight models that just made it hard for it to exploit successfully. And then replication is successful in most cases. If we look at a breakdown, this is where we can sort of see how maybe some of the pre-training has an impact on the performance of these models. So first, in terms of comparing vulnerabilities and weaknesses, I mentioned that one important aspect is that the agent is not only able to exploit sort of bugs in software that are well identified, but also human error, like misconfigurations, credential reuse, et cetera. If you look at the success rate for detecting, exploiting, both in terms of vulnerabilities and weaknesses, it's pretty consistent. So this is really important because it shows that the language model is not only able to adapt existing exploits to the specific machine in the case of these well-identified CVEs, but it's also able to form these exploits and generate these attack strategies in the case of human error from scratch. And so this is an important capability that's demonstrated here. In terms of the exploitation differences, we notice a big difference between Linux victims and Windows victims. In particular, when looking at privilege escalation, the agent was a lot more successful in escalating on Linux machines. And we hypothesized this is due to the different command line interface and the Linux command line just being a lot more friendly to language models. Similarly, we saw that the agent got a lot of challenges with web exploits. This is because you often need to traverse very sort of nested directories or nested HTML files, which the language model, the open-weight language model, was just not good at. So now, before I conclude, I wanted to share a few anecdotes. And this is really to show you sort of how important it is to have proper containment to do this kind of research. So one of the things that we had done is to implement a blacklist of IP addresses in the agent source code itself. The idea there is that we don't want the agent to sort of waste its time sort of attacking IP addresses that are outside our virtual environment, and this also adds sort of another layer of defense, if you want. What we found in one experiment is that the agent actually discovered this file in its source code and rewrote it to remove some of the IP addresses that were banned to be able to propagate to those. This didn't impact the sort of containment approach because, again, we enforced everything at the hypervisor level, but it shows how important it is to have that hypervisor level containment rather than something that's done at the level of what the agent can rewrite. We also found an instance where the agent realized that the containment attestation service included a client-side check. So the client-side check is just to verify that the agent is running within a virtual machine. And in some of our earlier experiments, that check sometimes would fail in certain operating systems. And so one of the agents that was trying to replicate to another machine for which the check was failing actually removed the check from the code to be able to replicate. And it did so successfully. And so again, this didn't impact our security because this is to prevent accidental launches, not to prevent propagation outside the environment. But it really shows sort of the ability to sort of tailor the attack strategy to respond to constraints encountered in the environment. And then there were some instances where the agent demonstrated some features that we had not explicitly hard-coded in the harness. One example is persistence. So we had not designed the agent in any way to be persistent once it gains access to a particular machine and replicates to it. But we found two examples where in one of them, the agent had registered its process with the service management system in the machine. And so that ensured that every time you would kill that process, it would restart. And then in another instance, the agent actually created a scheduled job to regularly launch itself on the machine. And so we observed these instances by trying to sort of clean up some experiments and try to stop all agent instances and notice that it would continue sort of replicating afterwards. So I think this really highlights the need, if we want to be able to do this research, to have this proper containment infrastructure around it. So to conclude, I'd like to make a few sort of recommendations for the academic community, but also beyond the academic community, the industry more generally. I think organizations need to realize that the patching sort of windows are getting a lot smaller than they already are. And so it seems like sort of penetration testing and fuzzing is more important than ever. And to be done at the scale that it needs to be done, it's very likely that it would be helpful to use AI in ways like what we've done in our work, but not to create a worm, but to assist with penetration testing and fuzzing. And again, when I started the talk, this is a lot of the motivation for the related work on this. Beyond discovering vulnerabilities, we need to put a lot more emphasis on patching and how to patch at scale. And then, of course, deploy techniques like zero trust or network isolation to limit sort of lateral movement once the agent has gained access to a particular environment. In terms of countermeasures specifically against these types of AI-driven worms, in our experiments, we noticed a lot of behavioral signatures that would help detection. So for instance, the use of SSH keys or leaving ports open that are very unusual ports, which could be used to detect the presence of this type of malware. But it's unclear to me how much these signatures are specific artifacts of the proof of concept that we design as opposed to inherent properties of AI-driven worms. And so I think here we'll need to do a lot more research on this to understand this. More broadly, beyond the specific topic of research, I think in this research really stress-tested a lot of institutional processes. And so we need more conversations in academia around sort of ethics and standards for how to do this kind of research. This will most likely be a multidisciplinary conversation. And there's a lot to be inspired from. So for instance, in communities working on biosecurity, they have dual-use review frameworks. And of course, the vulnerability research community has established coordinated disclosure norms that we can learn from. But this is something I think we can improve. And then maybe on a more cheerful note, because I know as security researchers, we often bring bad news to people. I found that this project really gave me a lot of hope that academics have a significant opportunity with open weight models The problems that we're tackling here are really complex and challenging, and the fact that we can do this within academia is really inspiring for me. And I think we need to really put a lot more emphasis on evaluating model capabilities beyond the closed source ecosystem, also within the open weight ecosystem. And these harnesses are really going to be a big part of that. We have to think of it as a system, not as just a model in isolation. And this is something that will require a lot of expertise that is within academia, sort of task-specific expertise. The last thing that I wanted to highlight is that open weight models are decentralized in nature. And so a lot of the AI governance and regulation conversation that we're having now is again centered on closed source models, which call for very different regulation mechanisms and very different governance mechanism. A very concrete example is that once we finish this research project, it's not clear sort of that there is a single entity that we should inform of this and they will be able to address this threat. This is really sort of something that's decentralized just by the nature of how we release these open weight models. And I think we need to have a conversation around this to start developing specific approaches for the governance and regulation of open weight models. And with this, I'll thank you for your attention. Thank again my students for their amazing work on this project, and our sponsors for making it possible. Thank you.
So when I was at HP a decade ago, Patch Tuesday would come along, and the patch would be deployed 6 months later. And the reason was it had to be tested against all the enterprise apps. Is there anything that now we could do to mitigate the worm attacks without potentially damaging enterprise apps? So is there something we can do faster than simply testing the patch against all the apps?
So in what ways would the enterprise apps be impacted in terms of the patches just impacting the utility?
A patch might break some legacy enterprise app that's been around for 30 years. Mm-hmm. And so they had to do the testing before they could deploy it to the company.
Right.
And so I was asking if your research could mitigate the access to the vulnerability by the worm while we were waiting for the patch to be deployed.
Well, I think one thing is that we should encourage sort of, we should separate sort of the sort of update streams for features and security updates to make sure that legacy devices can remain sort of secure for a longer horizon of time than they're supported for feature-wise. In terms of identifying sort of these negative consequences of patches on the utility of these applications, I think one thing we notice here is we're able to identify at scale a lot of the consequences of human error. So I gave examples of sort of SQL injection, credential reuse, and so on. And so I could imagine that you could use similar evaluation techniques to anticipate the consequences of deploying the patches, and sort of be at least aware proactively of what systems are going to be impacted if you deploy these patches. Yeah. Go ahead. I guess we can do one mic at a time.
Yes. Thank you, Nicolas. Thank you for this very exciting research. I'm curious about open source model, right? Did you do any fine tuning on that, or was it just a vanilla
Yeah, that's
model?
a very good question. So we didn't modify the open weight model in any way. And this was really because we wanted to show that it's an off-the-shelf model that doesn't require any fine-tuning, any sort of addition of knowledge specific to cybersecurity beyond what is provided by the structure the harness provides. And the same, just related to that, we didn't use any sort of closed source model APIs and so on that you could imagine adding that onto sort of the agent's sort of infrastructure when it encounters an API key or anything like that. It could use that, of course, to add on to its inference capabilities. We didn't do that because we wanted to show this thread is really isolated and sort of disconnected from what the closed source models are doing.
Can you share the model name? Or
we decided not to share it, but essentially it was released in 2025 and runs on A100, so 80 gigabytes of RAM.
Thank you.
Hi. This is a question out of curiosity, right? Like in your set of devices, you have chosen printers and whatnot. Like any reason why you have excluded smartphone?
We haven't excluded them specifically. We just haven't studied them. I think phones are designed in a way that the operating system is designed in a way that limits a bit the attack surface. But I don't want to speculate on sort of propagation to phones without actually running this as part of our experiments. Yeah, the only IoT devices we consider are cameras and printers. Okay. Yeah.
Hi, great talk. Yeah, I was wondering if you experimented at all with somewhat more adaptive sort of replication sort of methods, like whether if the GPU had more VRAM, the replication could happen with like a lower size model or something like this, and whether if you didn't think this is a possibility, it would be too complicated for the
Yeah, this is a good question. I think we would need to first understand sort of how generalizable the harness is to different models. We found in our work that when we tried using an even smaller model than the one we used, it was just not good enough in terms of long-term trajectories and the context window being too small. That said, I think this raises a good question in terms of the kinds of devices that will sort of support LLM inference. I think there's a clear trend in the industry that model size is decreasing and that hardware is also getting better at supporting LLM inference. So I anticipate the attack surface will just get bigger as time progresses. But yes, I think this and the previous question around sort of adapting the model to that specific task should sort of expand the attack surface.
Thank you.
Yep.
Do you know if any worms have been discovered in the wild that have an open-weight LLM embedded inside them, or doing anything similar to what you described in this research?
I don't, and I hope there are none. That was the whole point of the research.
Hey, hi, Nicolas. Great work there. You talked about not going towards the direction of using frontier models for offensive security, and yet I wonder, we see the Mexico breach, for instance, where frontier models commoditize offense exploitation. Also, the UK's AI Security Institute with ChatGPT 5.5. Are there any plans to compare the two in terms of effectiveness and economics, and what kind of approach might be one that we follow?
Yeah, I think my point is really that we've been ignoring a big part of the attack surface, with open weight models actually being very useful to malicious actors. Of course, the larger frontier models are also having an impact on cybersecurity in different ways, and sometimes the two can compound. So for instance, you could imagine that you use a larger model to discover new vulnerabilities and then deploy those at scale with an open weight model in something like an AI-driven worm. Yeah, I think in terms of the economics, like this runs on a single GPU, right? Mm-hmm. This is a very different resource level than the models that require an entire data center to run. And so I think we clearly are seeing sort of this capability being a commodity now for attackers. And that's the big reason for why we wanted to do this work, to alert people of that.
And it's a great piece of work. It's a great piece of work. I think, we need to continue comparing the two just to see, how
Absolutely.
As well. Thank you.
Yes, thank you.
Hi, I really like the recommendations you laid out for academia. And so I was wondering whether you can comment on how we can incentivize this. Like, should we put this in call for papers? Should we instruct reviewers to favor papers that use open weight models? Like, how,
So
how
let's
could we
also
use that?
fix the peer review system while we're at it. I think there are multiple instances of conferences that are starting to ask about this. So my bias sample of some of the conferences I was involved with. So for instance, at SATML, there was a recommendation to use open weight models when possible because that makes it easier to reproduce results. Something that is also sort of now in the call for papers at IEEE S&P. I think in terms of incentives, I mean, really what I see is, at least maybe in other parts of the world, there's a lot of talk of sovereignty that is impacting how academics are being funded and the type of work that's incentivized. And so I think in other countries that don't have sort of frontier model companies, there is a lot of emphasis on open weight models for that reason, because they decrease the dependency on these companies. Yeah.
Thank you.
Yeah.
Hi, thank you for the great talk. Like in your last slide, you made a recommendation. We need to think about ways to detect the inherent properties AI worms. I mean, if we treat this as a next generation of malware, we can think about EDR solutions or CM, right? Like, or IDSs. Like, where do you think our biggest leverages would be for this? Like one thing that I was, like one invariant, like the only invariant I can think of is, yes, like there needs to be an LLM invoked at the environment, like with some prompt. But that seems too general to turn into the detection. Like, but where did you think, like, if we think about the defensive solution for AI worm, where should we start? Like, at which granularity or level?
Yeah, I think one behavior we observed significantly is sort of the agent is very sloppy, and that it takes multiple trials to perform a lot of action. So it'll have a lot of typos in the commands that it's issuing and so on. And so most likely that's the kind of signature that is more inherent to sort of the fact that you're using especially a smaller language model. Then sort of it's less likely that humans would be as brute force in sort of their exploitation of these vulnerabilities. I think there is sort of this aspect of sort of the lack of precision makes this sort of more detectable in a sense. And then there is, of course, sort of the fact that you're having sort of this heavy reliance on language models creates a lot of signatures, both in sort of the usage of the resources to power these language models, but also in the fact you need to transfer the model's weights and so on. These are things that you would need to establish sort of covert channels for to be able to evade detection.
I see.
Yeah.
Thank you.
Yeah. I think we exhausted the question pool.
So, to
One more.
like, for you to go a bit further down on the question around like a blue team and what can be effectively done to more proactively study and potentially like defend against that type of threat, like in terms of footprint, live off the land by LM, because it's not very lightweight. So is there like some detector today that are actually catching those, or it's like new thing that need to be considered with those pretty much like heavy-footed LLM agent that will actually attack?
Yeah, I think the current proof of concept is easy to detect in the sense that it hasn't been designed in any way to be stealthy. And so the question as to whether or not this is easy to detect requires like another research project where we actually explicitly design the agent for stealthiness. And before we do that, I want to sort of carefully think about, is this the only way to study the problem, is to actually build something that is evading sort of detection mechanisms, because that is getting closer to building actual malware that can be deployed in the wild. So that's, I'm not entirely sure, and I'm happy to discuss this with people at the conference, sort of if there are ways to go about this in sort of the most responsible way possible. Yeah.
Awesome. Thank you very much, Nicolas.